copy of the notes. Okay. So, L'Hopital's rule. There is some variation in the spelling of L'Hopital. And sometimes it has a S, it looks like La Hospital, and sometimes they actually put an S in it, but it's not pronounced La Hospital. But if you call it La Hospital, I won't be mad at you. Just know it's not really supposed to be that, because sometimes that kind of helps you remember. Sometimes there are funny memes that are like, be careful taking limits, or you might have to go to La Hospital there, or something. I'll find a good one. I can't think of the one exact, but I believe, I think it's French. It is definitely not of English origin, that last name, and it is named after a mathematician that is credited for this, I believe. So L'Hopital's rule is actually for limits, but I could not teach you L'Hopital's rule whenever we were learning limits, because L'Hopital's rule requires you to be able to take a derivative, and when we were learning limits, we didn't know how to take a derivative yet. So really, anytime after we learned how to take a derivative, I could have taught you L'Hopital's rule, but I just stick with the order that they put it in the AP course exam thing. So, Unit 4 is on applications of differentiation. So I think this is just like an application. So it's not directly related really to anything else in Unit 4. Like, it's not really related to related rates or rates of change in functions that we've been looking at. It is kind of thrown in here. Thank you. Like I said, it really fits best with limits. This is a tool for solving limits, but we can't learn it because you have to know how to take the derivative first. So that's why it is not there. The good news is this makes some of the limit problems that we used to know how to do easier to do here. So one of the big things for L'Hopital's rule is kind of like intermediate value theorem or mean value theorem. There are conditions that must be true for L'Hopital's rule to be applied. So f and g have to be functions that are differentiable. You have to be able to take the derivative of f and g. They must be differentiable on some interval a through a to b that contains c, except possibly at c itself. These may not be differentiable at c, because at c, you can have a limit without having a derivative, right? You could have a hole in the graph but still have a limit there. So this does not, other than you have to be able to take the derivative, this is not all that important. You don't have to state this. You must assume that g prime of x does not equal 0. That is important because you can't have 0 in the bottom of a function here, except possibly at c itself. If the limit of f of x over f of g as x approaches c produces the indeterminate form, then we can say that the limit as x approaches c of f of x over g of x equals the limit as x approaches c of f prime of x over g prime of x. Okay, so the condition that we're going to have to make sure that we state is we've got to say that the limit of f of x over g of x gives you the indeterminate form 0 over 0. And there are going to be some specific ways we can do that I'll show you when we get to problems. Right? That has to be stated if it's a free response question. Obviously, if it's multiple choice, you can leave that part out. Provided that limit exists. This also is true for infinity over infinity. If you're getting infinity over infinity, that is another type of indeterminate form, in which case you could still apply L'Hopital's rule. Okay, so let's look at some problems. Okay, the first problem here, I'm going to do this problem the way that we used to be able to do it, and I'm going to do the problem using L'Hopital's rule. Okay, so we used to know how to do this problem. Perhaps some of us still do. If you saw this problem and you did not know L'Hopital's rule, what would you do to try to solve this problem? You can, but it's not going to get you anywhere. You plug in the 4, but if you plug in the 4 minus 4 is 0. You get 0 in the top. 4 squared minus 16, also 0. You get 0 over 0, which is indeterminate. It doesn't mean that you don't have an answer. It means you got to try something else. Not quotient rule, because this wasn't derivatives. There were a lot of different things that we looked at. This one, factor the bottom. Okay? So, the old way, we'll call this old way, which still works and is totally valid. Limit as x approaches 4 of 3 times x minus 4 over x minus 4 times x plus 4. Now what happens now that we have those factored? The x minus 4's cancel. You have a hole in the graph at that point, and holes don't matter for limits, right? You can have a hole at a limit. What do I do after that? Plug in 4, because now I'm not going to get 0 over 0. So I will have 3 over 4 plus 4, which will equal 3 over 8. Long ago, you guys were pretty good at this. Like if you saw that problem, most of you would have gotten it right. I should have given it to you as a warm-up to see if we could still get it right with no instruction now. I feel like our percentage of getting it right would be way lower than it was back in Unit 1, right? And this still works, and honestly, it probably is the easier way to do the problem for this one. But the good news about L'Hopital's rule is that L'Hopital's rule works on a lot bigger variety of problems. So we can use it for almost all limit problems they're going to give us. Not all limit problems, but almost all limit problems they're going to give us. And we don't have to think of like the different scenarios and rules. We can just apply L'Hopital's rule. So a lot of kids like once we learn this, it's kind of like the only way they do limits from here on out for the ones where it applies. So now the condition for L'Hopital's rule. So using L'Hopital's rule, this is the old way right here. Using L'Hopital's rule. I'm not even saying it's easier. I'm just showing you how to do it. If it is FRQ, you have to do the conditions. The condition is that the limit as x approaches 4 of this function has to give you indeterminate form 0 over 0. Now, I'm going to write something down that you may or may not want to write down, but it's bad notation, and we're not allowed to do it. Okay? I'll let you get away with it when we were doing limits. If you write limit as x approaches 4 of 3 times x minus 4 over x squared minus 16, and you plug in the 4, you would get 4 minus 4 over 4 squared minus 16. And that would give you 3 times 0 over 16 minus 16, which would equal 0 over 0. But they do not, I think I mentioned this when we were doing limits, but I kind of let you get away with it here. They do not like for you to ever say that anything equals 0 over 0. 0 over 0 is the indeterminate form. It's not a number. It's not anything except it's like a I don't know. It's kind of like you put this equals IDK right here. You don't get points for IDK, right? So mathematically it's bad to say that. So there are 2 ways around this. So proper notation for this. This is what I prefer for you to do. You're going to do the limit as x approaches 4 of the numerator only. which is going to be 3 times 4 minus 4, which is going to give you 0. And then you're going to do the limit as x approaches 4 of the denominator only, which is 4 squared minus 16, which gives you 0. So you're doing the limit of the top and the limit of the bottom separately and saying that each one of those equals 0. So you didn't say anything was equal to 0 over 0. You just said the limit of the top was 0 and the limit of the bottom was 0. And then you could say, therefore, L'Hopital's rule applies. Okay, your other option for this is to, I'm using up too much room here, but that's okay. Your other option for proper notation for your conditions here is to say limit as x approaches 4 of, you can do the whole thing. You can go here. You could even go like this far, and you could say is of the indeterminate form 0 over 0. So you can either do this or do this to meet your notations, but you don't want to say equals 0 over 0. That's bad notation. Depending on how they set up the points for the problem, you'll miss a point if you put equals 0 over 0 on some of these. Now, this is all conditions. This is all FRQ stuff, right? The actual solving of the problem, here's what you are going to do. I realize I am using up way too much space. You are going to do limit as x approaches 4. Now this time I am going to go ahead and distribute that 3x minus 12 over x squared minus 16. And then I'm going to say this is going to equal the limit as x approaches 4. You're going to take the derivative of the top and the derivative of the bottom. This is not a quotient rule. You are not taking the derivative of this function. You are taking the derivative of 3x minus 12, which is 3. Right? You're taking the derivative of x squared minus 16, which is 2x. Then you can plug in 4, 3 over 2 times 4, which will equal 3 over 8. Okay. I'm not even saying it's easier. It just works in more scenarios, right? It will work for things like example 2. Now, how would we solve example 2? This is a Bobo-Botno because x approaches infinity, right? So this one is bigger on the bottom, and you would get 0. That's the best thing to do here, honestly. But you can also do L'Hopital's rule for this. If we do L'Hopital's rule, we're starting off with some ones where there's actually easier ways to work to ones where you got to do L'Hopital's rule. So I would say the limit as x approaches infinity of 2x minus 7. Now, what's going to happen if I plug infinity in here? You're just going to get positive infinity, right? And the limit as x approaches infinity of 3x squared minus 9. What's going to happen if I plug infinity in here? Still infinity, because even if I subtract 9 from infinity, it's still infinity, right? So we're actually getting indeterminate form of infinity over infinity here, which they may give to you. But either way, L'Hopital's rule applies. Okay, that's the requirements if it is a FRQ. Then you are going to take the derivative, limit as x approaches infinity of, well, I guess we really should do 2x minus 7 over 3x squared minus 9, and then that equals the limit as x approaches infinity of 2 over 6x. So for this, you're not going to get infinity over infinity, right? You can't really plug in infinity. It's bad to plug in, like, don't do 2 over 6 times infinity. It's also kind of like bad notation to show. But if x approaches infinity, if x gets bigger and bigger and bigger and bigger and bigger, what's going to happen to the value of that fraction? Smaller and smaller and smaller and smaller, closer and closer and closer and closer to 0, right? So this will approach 0 for that. Yes. If you saw this, it would be best to answer it with Bobo-Botno. In which case, you can probably just say equals 0. You probably do not have to show any work for that. So they would just expect you to understand that. So it is better for you just to do that. In order for me to get, like, they may give us, I'm trying to think of a way, the way that they might make it L'Hopital's rule is they might give you, like, they don't actually give you the top and bottom of this function. They might call the top of it like f of x or something. And then you have to, like, piece things together because you can't just look at the equation. So this one is definitely quicker and easier, Bobo-Botno, and probably wouldn't require explanation. But L'Hopital's rule could be used. Now, both of these, I would not necessarily say L'Hopital's rule makes anything easier. Let's go over here. Now, you could do this the old way. I am going to say that, just tell, I'm not going to go through it. It takes too long. What do you have to do if you do this the old way? If you got that square root right there. You multiply by the conjugate, right? So it's like, we'd have to multiply top and bottom by the square root of 25 minus x squared plus 5. Right, and those were kind of hard. Those were harder than the other two that we did. So a new option. Now, if it is, I'm gonna do one more where I treat it like a FRQ. Right, I'm gonna do limit as x approaches 0 of the square root of 25 minus x squared minus 5 is going to be the square root of 25 minus 0 squared minus 5. Which is square root of 25 minus 5, which just gives you 0. All right, and then we'll do the limit of the bottom separately. Well, that's just the limit as x approaches 0 of x. That's clearly just 0, right? And then we could say, therefore, L'Hopital's rule applies. Now, that square root right there, let's think of that as like this to the 1/2 power. That'll make it easier for us to take the derivative. So we could say the limit as x approaches 0. We've got to do a chain rule here. So we'll have 1/2 25 minus x squared to the negative 1/2 times the derivative of the inside. What is the derivative of the inside of that square root? Almost 2x. Negative 2x. And then what's the derivative of that minus 5 over there? That's just 0. It goes away when we take the derivative. So top is complicated, but what's the derivative of the bottom? It's just 1. So, like, part of our issue's gone away here, right? So we could say this equals, don't drop your limit notation yet because you haven't plugged in 0. I'm going to, like, simplify this a little bit to make it easier to plug in. 1/2 times negative 2 is going to give me negative 1x. And then I'm going to send the 25 minus x squared to the 1/2 down to the bottom. So that'll be square root of 25 minus x squared. Okay, now I can just plug in 0. I get negative 0 over the square root of 25. What's happening here? Minus 0 squared, which is going to be 0 over square root of 25, which is 0 over 5. What does that equal to? 0. So 0 is your answer for that problem. That, I think, is at least probably as easy as doing it the other way for that. Let's go down to 4. Now 4, we really start to get into a scenario where clearly if I plug in 1, I get 0 over 0. I do know how to factor x to the 4th minus 1, because it'd be like x squared minus 1, x squared plus 1, and then you could factor your x squared minus 1 into x minus 1, x plus 1. I do know how to factor that. There probably is a way to factor x to the 11th minus 1. I do not know the rules for factoring something to the 11th power. That works for expanding. So that would be like if you have like x minus 1 to the 11th power. So you couldn't use Pascal's triangle here. Like I said, there's probably a rule, but I don't know it. So this is where L'Hopital's rule becomes pretty much essential, right? So I'm getting 0 over 0. If this was a free response, I would write out all of that stuff, right? I'm going to skip it for sake of time. So L'Hopital's rule applies. I can do the limit as x approaches 1 of 11x to the 10th. Derivative of the minus 1 is just 0, so that goes away. On the bottom, I'm going to get 4x to the 3rd. And then, if I plug in 1, I get 11 times 1 to the 10th over 4 times 1 to the 3rd, which is just going to be 11 over 4. And so without knowing some extensive factoring rules that they probably only teach to Chinese geniuses over there or something, like, without knowing that stuff, L'Hopital's rule is the only way to do the problem. And even if you did know how to factor 11, x to the 11th minus 1, L'Hopital's rule would be easier, right? So that's going to be our best bet. Okay, so a lot of these turn out to be not that bad, really, here. So, for example, if I plug in, you can't really plug in infinity, but if I thought about plugging in infinity here, e to the x is going to be, that's going to go to infinity, and infinity to the 3rd also going to go to infinity, right? So I've got infinity over infinity here. Now, you can use a Bobo-Botno on this, sort of. Which one's this one going to be? Is it bigger on top, bigger on bottom? Definitely not exponents are the same, right? What? Bigger on top. E to the x counts as higher than any x to any power. But maybe we forgot that. If we forgot that, we could use L'Hopital's rule. So L'Hopital's rule, like, allows us to do the problem even though we've forgotten a lot of the real limit rules, right? Because this one ends up being one where you're going to have to do this more than once. I can do limit as x approaches infinity. What's the derivative of e to the x? E to the x. What's the derivative of the denominator? 3x squared. That still gives me infinity over infinity. I could do it again. Limit as x approaches infinity. E to the x remains e to the x. It is its own derivative. But here I get 6x. still I would get infinity over infinity, right? But if I do this one more time, limit as x approaches infinity, I get e to the x over 6. Now, if I have e to the x, that value is going to approach infinity. And if I take infinity and divide it by 6, it's still infinity, right? So this can help us know what to do if possibly we've forgotten our rules, right? Now, you also could just straight say infinity from the beginning on this using no rules. But L'Hopital's rule can be helpful. For number 6, we're running into some trig here. I feel like maybe there's a trig identity, but we got the 5x and the 9x. There might be a way this can be done a different way. But first of all, let's check and make sure. I do want to make sure L'Hopital's rule applies here, because there's a chance it doesn't, and that I need to solve this a different way. So let's treat it, and it's not. This one's a little harder to think through. So let's go through the motions here. Limit as x approaches 0 of sine of 5. X is going to equal sine of 0 and unit circle. Sine is my y coordinate. At 0, I will get 0, right? Limit as x approaches 0 of tangent of 9x is going to be tangent of 9 times 0, which is just not tangent of 0. Tangent of 0 is sine of 0 over cosine of 0. So we're going to get 0 over 1 here, which would still be 0. So L'Hopital's rule applies. You need to at least think through that. If it's free response, you need to write it down. Since L'Hopital's rule applies, we're just going to take the derivative of the numerator and the denominator. So what is the derivative of sine? Cosine. But what else do I have to do with this? Multiply it by 5. I'm going to write it out front here. Okay? What's the derivative of tangent? Secant squared. But what needs to go with it? 9, because this is a chain rule here. Okay, so once I've taken the derivative, most of the time, like we do have problems like number 5 where we might have to take the derivative a few times. But most of the time you can plug in after that first derivative. So we would have 5 cosine of 5 times 0 over 9 secant squared of 9 times 0. So what is cosine of 0? 1. So this is going to work because we're not getting 0 in the top, right? Even if we get 0 in the bottom, we can have an answer for this. Now secant, I'm going to write it this way. Secant of 0 squared is what we're looking at here. Secant is 1 over cosine of 0. What is cosine of 0? 1. So 1 over 1 squared, all of that still equals 1, right? So we get 9 times 1, and we get 5/9 for our answer. Okay, we are much better, I believe, at taking the derivative of a basic trig function than we are at remembering all those trig identity rules and flipping and multiplying. And in this case, you got different 5x's and 9x's. It would be tough. Okay, questions here? Okay, now, here's another one. We could do this with our rules. There was a rule where the limit as x approaches 0 of sine x over x equals, anybody remember it? it was 1 for that. But you would have to remember that. And the likelihood that you remember it is probably pretty low. So if you run into this, you can use L'Hopital's rule instead, because sine of 0 is 0. So you're going to get 0 over 0 for this one. So now we've got to use a product rule for that numerator. So we'll have the limit as x approaches 0 of product rule in the numerator, sine x times the derivative of cosine x, which is negative sine x, plus cosine x times the derivative of sine x, which is cosine x, all over the derivative of x. What's our derivative of x? 1. So if we want to simplify this a little bit, that is negative sine squared x plus cosine squared x over 1. We are going to be doing well, I can go ahead and plug in now. That's going to be negative sine squared 0 plus cosine squared 0 over 1 if you want to keep writing that. What's sine of 0? 0. So you got 0 squared, negative 0 squared technically, but we don't need the negative there. And cosine of 0 is 1 squared, and so that gives you 1 for that. So 1 would be our correct answer. Okay, here. All right, let's look at a few of the ways. So these, you've got, most of these you have options. We only really looked at one where we had to use L'Hopital's rule. You have options, but L'Hopital's rule can replace a lot of those other rules that you already knew. There are some ways the AP will give you where you have to use L'Hopital's rule. Okay, for example, number 8. The graph below shows the graph of f. The line tangent to the graph of f at x equals 0 is also shown. We are supposed to find the limit as x approaches 0 of 2f of x e to the x plus 4 over 3x squared minus 3x. My advice to you on these problems, always treat it like it's going to be a L'Hopital's rule if you see something like this. It might not be. It could be like a direct substitution problem, but you'll figure that out as you go through it like a L'Hopital's rule problem, right? So if it's L'Hopital's rule, we need to do, like we're talking FRQ L'Hopital's rule, do the limit of the top and limit of the bottom. Make sure you're getting 0 over 0 or infinity over infinity. So I'm going to do the limit as x approaches 0 of 2f of x e to the x plus 4, and you're just plugging in 0, so 2f of 0 e to the 0 plus 4 is going to be f of 0. What is f of 0 on that graph? Negative 2, which is the y coordinate at that point that's marked there, so it's negative 2. What is e to the 0? 1 plus 4, we're getting negative 4 plus 4, which is 0. So the limit of our numerator is 0. We also want to do the limit as x approaches 0 of the denominator, which is going to be 3 times 0 squared minus 3 times 0, and you probably don't even have to show the work for that. You can tell that's going to be 0. So we are getting 0 over 0 when we plug into this function. So we could say L'Hopital's rule applies. I think you can get by with it if you just go ahead and apply it. I don't think you have to call it by name. I think it's a good practice to call it by name. I think you're going to have some like college professors that might require that. So like especially if you ever find yourself going beyond this class, I think it's a good idea to do that there. So, but the limit stuff right there definitely has to be done. So we can say that the limit as x approaches 0 of 2f of x e to the x plus 4 over 3x squared minus 3x. We can take our derivative of the top and the bottom. You're not using a quotient rule here. You're just taking the limit of the top and the bottom separately. But what do I need to take the derivative of 2f of x e to the x plus 4? Got to use a product because I got the f of x times the e to the x, right? So I'm going to have 2f of x times the derivative of e to the x, which is just e to the x, plus e to the x times the derivative of 2f of x. What is that? 2f prime of x. Okay, so that takes care of this part of the derivative. What's the derivative of that plus 4? 0. It goes away, right? This is all over 6x minus 3. And then typically, what's going to happen is now if you plug in 0, you'll get the right answer. So we'll have 2f of 0 times e to 0 plus e to 0 times 2f prime of 0 over 6 times 0 minus 3. And so f of 0, we already said, is negative 2. E to the 0 is 1. This e to the 0 is also 1 times 2. What's f prime of 0 going to be? It is negative 1. How do we know that, Michaela? Slope of that tangent line, right? Because that's the reason they put that tangent line there for you, so you could count its slope, and that tangent line has a slope of negative 1. So all this is over negative 3. Technically, if it's FRQ, you could stop here, but this isn't that difficult, so let's finish out here. Negative 4 minus 2 over negative 3. So we're going to get negative 6 over negative 3, which will give us a positive 2. You're forced into L'Hopital's rule in this case. There's no other way to solve it, given what they have given you for this problem. The last one there is also another way for them to force you into using L'Hopital's rule. I am just, if we plug in extra, negative 1 right here, we got 2 times negative 1. F of negative 1 is 5. So that's going to be negative 10. Here, this is going to give us positive 10. We'll get 0 over 0. You should, on an FRQ, show that that happens. But since we are about to run out of time, I'm not going to write all that down. So I'm going to go straight to L'Hopital's rule here. The derivative of 2x times f of x minus 5g of x, you got to do a little work here, right? This is going to take a product rule on that first part. 2x times f prime of x plus f of x times the derivative of 2x, which is 2. Now that right here, this is the derivative of this, but you must also do the derivative of 5g of x. 5 is just a coefficient, though. We don't need a product rule here. So we're going to have minus 5g prime of x all over. The derivative of the bottom is just 1. And so to solve this, we just got to plug in negative 1. So we got 2 times negative 1 times f prime of negative 1 plus f of negative 1 times 2 minus 5g prime of negative 1. Now, if it's free response, you cannot stop here. You have to replace all of your f ofs and g ofs here. So you're going to have 2 times negative 1. F prime of negative 1 is 1. I'm pulling that from the table right here. F of negative 1 is 5 times 2. And then I got minus 5 times g prime of negative 1 is going to be 4 here. On an FRQ, you could stop here. But let's just simplify it because we might see these here as multiple choice. So that's going to be negative 12, I believe, there for that, for our answer.